the summer of 1952, over the Yellow Sea, a piston-engined aircraft shot down a jet. The pilot was Lieutenant Peter Carmichael of 802 Naval Air Squadron, Fleet Air Arm. His aircraft was a Hawker Sea Fury, a propeller-driven fighter designed in the final years of the Second World War. The engine turning that propeller was a Bristol Centaurus 16, producing 2,080 horsepower through 18 cylinders, arranged in 2 radial rows behind a single reduction gearbox. Carmichael closed on a MiG-15, a swept-wing Soviet jet capable of 670 miles per hour, and opened fire. The MiG went down. It was one of the last confirmed victories of a piston-engined aircraft over a jet fighter in the history of air combat, and it should have been a moment of vindication. It was not. At the moment Carmichael's guns fired over the Shanghai coast, the Bristol Aeroplane Company's Patchway Engine Division had already received its instructions. No new Centaurus production orders would follow the 1953 batch. The Air Ministry had made its decision quietly. No white paper, no common statement, no public announcement of any kind. Britain was going all jet. The most powerful air-cooled piston engine ever built in the United Kingdom was being wound down in peacetime Bristol while it was still winning fights in wartime Korea. The program did not end in failure. It did not end in scandal. It ended in administrative silence. At the precise moment, the engine reached the peak of everything it had been designed to become. But the real story of the Bristol Centaurus is not the silence of its ending. It is the story of how Britain's most technically ambitious aero engine was retired at its peak, and how the company that built it spent its final productive years financing its own replacement. By the mid-1930s, the Royal Air Force was running out of answers. The biplane era was ending. Germany was rearming openly, and the aircraft emerging from its factories. The Messerschmitt Bf-109, the Heinkel Heer 111, were monoplanes capable of speeds that British fighters could not match. In 1935, the Air Ministry launched Expansion Scheme C, a program of accelerated rearmament that demanded a new generation of combat aircraft. Fighters capable of exceeding 300 miles per hour. Bombers capable of carrying meaningful payloads to meaningful distances. The engines powering the current fleet, the Bristol Mercury, the Bristol Pegasus, both proven and reliable radials, were approaching the ceiling of their design. They could not be stretched far enough to meet what the Air Ministry now required. The gap was not marginal. It was structural, and it fell to 3 British companies to close it. Rolls-Royce at Derby was developing the Vulture, a 24-cylinder X-configuration engine of enormous complexity. Napier at Acton was working on the Sabre, a 24-cylinder H-configuration engine also of enormous ambition. And Bristol, at its Patchway Engine Division on Filton Road on the northern edge of Bristol, was pursuing something that most of the British aero engineering establishment regarded as a dead end. The Bristol Aeroplane Company had been founded in 1910 at Filton, originally as an aircraft manufacturer. By the early 1930s, its engine division, operating from the Patchway Works, a separate facility approximately 1 mile north of the main Filton airframe factory, had established itself as one of the 3 dominant aero engine producers in Britain. The Jupiter, designed in the early 1920s, had powered aircraft in 26 air forces. The Mercury and the Pegasus had refined the air-cooled radial formula across 2 generations of RAF bombers and fighters. Patchway, by 1935, employed approximately 3,000 engineers and skilled machinists. It was a serious place, doing serious work. The man responsible for that work was Roy Fedden. Fedden had joined the predecessor organization in 1906 as a draftsman, having left school at 16 with no formal engineering qualification. What he lacked in academic credentials, he compensated for in an obsessive precision about mechanical reliability, a characteristic that shaped every engine that left Patchway under his direction. By 1935, he had been chief engineer of the Bristol Engine Division for 15 years. The Jupiter, Mercury, and Pegasus were his programs. Their record in RAF and Commonwealth service was his argument. And in 1935, Fedden made a decision that his contemporaries at Rolls-Royce and Napier considered at best premature and at worst impossible. He chose the sleeve valve. The conventional aero engine of the period used poppet valves, mushroom-shaped metal discs driven by a camshaft, opening and closing the ports through which the fuel-air mixture entered the cylinder and through which exhaust gases left it. The system worked. It was understood. Every major aero engine manufacturer in the world used it. But by the mid-1930s, poppet valves were approaching a thermal boundary. At the power outputs and compression ratios the Air Ministry now required, the valve heads were running hot enough to cause pre-ignition, the uncontrolled detonation of the fuel mixture before the piston reached the top of its stroke. Pre-ignition damaged engines. It limited power. It set a ceiling. Fedden's alternative was the sleeve valve, a thin cylinder of hardened steel fitting between the piston and the outer cylinder wall that slid and rotated in a precisely controlled pattern during each combustion cycle. At the correct moments, ports machined into the sleeve aligned with corresponding ports in the outer cylinder, opening the intake and exhaust passages without any separate valve mechanism at all. No poppet head to overheat, no valve spring to fatigue and fail. A combustion chamber geometry, hemispherical, with the spark plug at its apex. That was thermodynamically superior to anything a poppet valve layout could achieve. 3 Air Ministry consultants reviewed Fedden's proposal in 1936. All 3 concluded that manufacturing a sleeve valve to the tolerances required, clearances measured in thousandths of an inch, could not be achieved in series production with existing British machine tool technology. Fedden noted their conclusions. He proceeded regardless. The development contract for what would become the Bristol Type 57, the Centaurus, was awarded in 1936, valued at £175,000, equivalent to approximately £14 million at current prices. The design specified 18 cylinders in 2 rows of 9, all sleeve valve, all air-cooled, arranged around a central 2-piece aluminium crankcase. The target output, 2,000 horsepower, more than any Bristol engine had previously produced. More, at the time of contract award, than any air-cooled radial engine in the world had reliably sustained. Prototype construction began at Patchway in late 1936. 4 competing designs were in development across the British industry simultaneously. Only one of them would solve the manufacturing problem that all 4 shared. Only one would reach the squadrons without a structural catastrophe. That engine was the Centaurus. The first full bench run of the Centaurus prototype took place at Patchway in April 1938. The engine ran, it produced power, and then at sustained high temperature, the sleeves seized. The clearance between sleeve and cylinder wall, 0.001 inches, a gap narrower than a human hair, was collapsing under thermal expansion. The steel was growing. The oil film between the surfaces was breaking down. The sleeve, instead of sliding and rotating in its controlled pattern, was locking against the cylinder wall with enough force to stop the engine. It was precisely the failure that Fedden's critics had predicted, and it was precisely the problem that Fedden's team now had to solve. They solved it in 3 stages. First, the oil feed galleries supplying lubricant to the sleeve surfaces were redesigned, enlarged, repositioned, and pressurized to maintain film integrity at temperatures the original design had underestimated. Second, the sleeve material itself was subjected to a proprietary nitriding process developed entirely within Patchway, a heat treatment that hardened the steel surface to a depth of a few thousandths of an inch without distorting the dimensional accuracy on which the entire system depended. Third, Bristol commissioned the construction of dedicated grinding machines, designed and built at Patchway, capable of finishing sleeve bores to tolerances that no commercially available British machine tool could hold. The existing industry could not manufacture what Fedden had designed. So Fedden's engineers manufactured the machines that could. By late 1938, the seizure problem was under control. In December of that year, a Centaurus was installed in a modified Bristol Beaufighter airframe at Filton for initial flight testing. The combination was ungainly. The Centaurus's 55.5-inch diameter demanded a significantly wider nacelle than the Beaufighter's standard Hercules installation, but the purpose was not elegance. It was data, hours, temperature cycles, the accumulation of evidence that the sleeve valve, at altitude and under load, would hold. It held. To understand what the Centaurus represented in physical terms, it is worth pausing on the numbers. 18 cylinders, each with a bore of 5.75 inches and a stroke of 6.5 inches. Total displacement, 3,170 cubic inches, roughly the combined displacement of 3 large American V8 car engines. Dry weight, 2,195 pounds. Yet the engine's frontal diameter, at 55.5 inches, was only marginally larger than the Bristol Hercules it was designed to succeed, itself no small machine. The sleeve valve layout, by eliminating the overhead valve gear that a poppet valve engine of equivalent displacement would have required, allowed Bristol to pack 18 cylinders into a frontal area that a conventional design would have struggled to accommodate with 14. Output, in the initial production, Centaurus I of 1942 stood at 2,000 horsepower at takeoff. By the Centaurus XVI of 1944, that figure had risen to 2,120 horsepower. The final development variants reached 2,050 horsepower at specific boost settings, a figure that represented the absolute ceiling of what an air-cooled piston aero engine could reliably produce in British series manufacture. Nothing built at Patchway, at Derby, or at Acton would ever exceed it in production. While Centaurus was finding its footing, its rivals were collapsing. The Rolls-Royce Vulture, the 24-cylinder X-configuration engine selected to power the Avro Manchester bomber, suffered a series of catastrophic connecting rod failures in squadron service from 1941. The Vulture program was abandoned. The Manchester was redesigned around 4 Merlin engines and emerged as the Lancaster. The Vulture's failure cost Rolls-Royce 2 years and considerable institutional credibility in the high-power engine competition. The Napier Sabre, the rival sleeve valve program using a horizontally opposed 24-cylinder H configuration, was simultaneously tearing itself apart in Hawker Typhoon squadrons. Sleeve seizures and persistent lubrication failures kept Typhoon's serviceability rates below 60% through much of 1942 and into 1943. The Sabre eventually matured, but only after years of crisis management that consumed Napier's engineering resources and severely damaged the Typhoon's early operational reputation. Centaurus, by 1943, was posting squadron serviceability rates above 85%. The problem declared unsolvable in 1936 had been solved, completely, in series production, by a workforce in Bristol that had built the machine tools to do it themselves. The Air Ministry had its engine. Now it needed the aircraft to carry it. By 1944, the commitments were substantial. Hawker Aircraft at Kingston had designed both the Tempest Men K2, a land-based fighter bomber, and the Sea Fury, a naval strike fighter intended for carrier operations, around the Centaurus. Westland at Yeovil had committed the Wyvern, a strike aircraft for the Fleet Air Arm, to the engine's early marks. Bristol's own Brigand and Buckmaster programs added further to the order book. At peak, Patchway was running at approximately 90 engines per month, with a direct workforce of 600–800. Subcontractors across Bath, Swindon, and the South Wales valleys, supplying castings, forgings, bearings, and machined components, accounted for an estimated 4,000 additional workers. 12 airframe programs, 14 distinct aircraft types, at various stages of development or production, were linked to the Centaurus by the end of the war. It was the broadest single-engine dependency in British aviation history. And then the war ended, and everything that dependency had protected began, quietly, to unravel. Between 1942 and 1957, approximately 2,500 Bristol Centaurus engines left the Patchway works. At peak production in 1944 and 1945, the line was turning out roughly 90 engines per month, a rate sustained by a workforce and a subcontractor network that had rebuilt itself around a single engine's requirements. The Centaurus powered 14 distinct aircraft types across its production life. It served in the air arms of Britain, Canada, Australia, Pakistan, Iraq, Egypt, and Cuba. It flew from carriers and from jungle airstrips. It flew ground attack missions and anti-shipping patrols and close air support sorties over terrain that would have challenged far more modern machinery. But it is in Korea, in the summer of 1950, that the full measure of what the Centaurus could do becomes most clearly visible. When North Korean forces crossed the 38th parallel on 25th of June 1950, the Fleet Air Arm's frontline carrier aircraft was the Hawker Sea Fury FB-11, a single-seat strike fighter powered by a Centaurus Textinte developing 2,180 horsepower at takeoff. The Sea Fury was, by any objective measure, the finest piston-engined fighter ever to enter Royal Navy service. Its top speed of 460 miles per hour made it competitive with early jet fighters at low and medium altitude. Its range, approximately 700 miles on internal fuel, gave it an endurance over the target area that the Seahawk and Attacker jets entering service elsewhere in the Fleet Air Arm could not match. And its Centaurus engine, operating in the salt air and humidity of the Yellow Sea, proved more tractable in shipboard maintenance conditions than any jet power plant then available to the Royal Navy. HMS Theseus deployed to Korean waters in October 1950 with 807 Naval Air Squadron embarked flying Sea Furies. Over the following 7 months, 807 NAS flew 2,044 operational sorties, ground attack, armed reconnaissance, rail interdiction, and close air support for United Nations ground forces along the western Korean coast. The Centaurus engines powering those sorties accumulated thousands of hours in conditions the Patchway test engineers had never specifically anticipated. Salt-laden air, wide temperature swings between the cold of the Sea of Japan and the heat generated by sustained combat power settings, and the mechanical violence of repeated arrested landings on a carrier deck operating in winter swells. The engines held. HMS Ocean relieved Theseus in May 1951 with 802 Naval Air Squadron embarked. 802 NAS continued the pattern. Interdiction, close support, the relentless grinding work of a carrier air group operating in a confined theater against a well-supplied enemy. And it was during Ocean's deployment that the Centaurus achieved the distinction that no amount of peacetime testing could have manufactured. On 9th of August 1952, Lieutenant Peter Carmichael of 802 NAS was leading a flight of Sea Furies on a combat air patrol over the Hwanghae coast when the flight was intercepted by a formation of MiG-15s. The MiG-15, a swept-wing turbojet fighter supplied to North Korea by the Soviet Union, was faster than the Sea Fury at altitude by a margin of over 200 miles per hour. It climbed faster. It accelerated faster. By every measure of raw performance, it should have been untouchable by a propeller-driven aircraft. Carmichael maneuvered inside the MiG's turn radius, the one domain where the Sea Fury's lower wing loading gave it an advantage, and fired. His cannon shells struck the MiG. It went down. The engagement was confirmed by gun camera footage and corroborating witness accounts from the other Sea Fury pilots in the formation. It entered the record as one of a small number of confirmed kills of jet aircraft by piston-engine fighters in operational history, and almost certainly the last such engagement ever conducted by a Royal Navy aircraft. What made it possible was not luck. It was the Centaurus, a jet-powered aircraft in the same situation, with the fuel consumption rates of the early Rolls-Royce Nene or de Havilland Ghost, would have had perhaps 12 to 15 minutes of combat fuel remaining at the point of interception. The Sea Fury, with its Centaurus running at combat power, had considerably more. The margin of endurance gave Carmichael the time to maneuver. The power of the engine gave the aircraft the energy to sustain those maneuvers through multiple turning engagements. The Centaurus did not make the kill inevitable, but it made the kill possible. Beyond Korea, the operational record spread across 3 further theaters. In Malaya, From 1950 onwards, No. 45 Squadron RAF and No. 84 Squadron RAF operated the Bristol Brigand MB Dun 1, a twin Centaurus strike aircraft from RAF Tengah in Singapore against communist insurgent positions in the jungle interior. The brigand's role was low-level rocket and cannon attack on jungle clearings, supply routes, and identified insurgent camps. At low altitude, in high humidity, and temperatures regularly exceeding 35 degrees Celsius, the Centaurus performed without the thermal management problems that plagued early jet engines in tropical conditions. Jet engines of the period burned significantly more fuel at low altitude than at their optimum cruise height, a characteristic that cut their effective range and loiter time over target by margins that made sustained close air support operations logistically demanding. The Centaurus, optimized for low-altitude power output, carried its payload further and stayed over the target longer. No. 45 Squadron flew brigand operations in Malaya until 1952, when the aircraft was withdrawn, not because the Centaurus had failed, but because the brigand airframe had accumulated structural fatigue issues in the low-level environment for which it had never been fully stressed. The engine outlasted the aircraft that carried it. In the Canal Zone and during the early stages of the Suez Crisis, Sea Furies from the Royal Egyptian Air Force, which had taken delivery of Centaurus-powered aircraft in the late 1940s, were encountered by Israeli Spitfires over the Sinai in 1948. The operational complexity of that encounter belongs to a different story. What it confirmed was that the Centaurus had reached air forces beyond the Commonwealth, a measure of the engine's reputation that Bristol's export sales team had worked systematically to build since 1946. The Royal Canadian Navy operated Sea Furies from HMCS Magnificent with 803 Squadron embarked from 1948. The Royal Australian Navy's 805 and 808 squadrons flew Sea Furies from HMAS Sydney. The Royal Pakistan Air Force received Fury variants. The Iraqi Air Force, the Cuban Air Force, by the early 1950s, the Centaurus was operating on 5 continents. At Patchway, the peak years felt permanent. The factory floor covered 1.2 million square feet. The directed workforce of 6,800 was supplemented by a supply chain that reached into nearly every engineering town in the West Country and South Wales. Members of Parliament for Bristol North West and Bristol South East both understood, with the clarity that constituency economics provides, that Patchway's order book was not an abstract defence matter. It was employment. It was rates revenue. It was the wage packets of the men who voted for them. But inside the Air Ministry, the arithmetic was changing. The de Havilland Vampire had entered widespread RAF service in 1948. The Gloucester Meteor had been in frontline use since 1944. The Hawker Hunter was on its way. Each new generation of jet aircraft rendered the performance case for piston-engine fighters a little weaker, a little harder to argue in the committee rooms of Whitehall and inside Patchway itself. The change was visible in the most unambiguous possible way. The engineers who had spent the war mastering the sleeve valve were now, under the direction of Stanley Hooker, who had joined Bristol from Rolls-Royce in 1949, spending their afternoons on drawings for a turbojet. The Olympus program had begun. In the financial year 1949 to 1950, Centaurus orders from the Air Ministry reached their peak. In the financial year 1950 to 1951, they declined. In 1951 to 1952, they declined again. No announcement accompanied the reduction. No ministerial statement explained it. The order book simply shrank, one contract cycle at a time, while the aircraft it powered continued to fly combat sorties over Korea and jungle clearings over Malaya. The engine that had taken 16 years to perfect was being quietly set aside, and almost no one in the country that built it knew. There was no single moment. That is what makes it difficult to fix in the historical record with the precision that a formal cancellation, a common statement, a white paper, a named minister at a dispatch box would have provided. The Bristol Centaurus was not cancelled. It was allowed to expire. And the distinction matters because expiry leaves fewer documents, generates less parliamentary debate, and produces almost no public record of the reasoning that drove it. What the available evidence establishes is this. By 1952, the Air Ministry had arrived at a policy position, not yet formalized in a published white paper, but circulating in internal papers now held in the AVIA series at the National Archives, Kew, that all first-line RAF combat aircraft were to be jet-powered by 1957. The decision carried an implicit corollary. No new development contracts for piston aero engines intended for combat aircraft would be issued. The Centaurus was not named in those papers as a program to be terminated. It simply ceased to appear in the forward-planning documents as a program with a future. The official reasoning, where it was articulated at all, pointed to performance. Jet engines offered superior speed at altitude, greater growth potential, and an operational ceiling that piston engines could not approach. These arguments were correct as far as they went. At 40,000 feet, the Centaurus was irrelevant. Against a Soviet jet interceptor in the stratosphere, a Sea Fury was not a credible response. But the official reasoning did not go far enough to be the whole truth, and the procurement historians who have examined the AVA files in the decades since have noted what the Air Ministry's internal papers carefully avoided stating. That in the operational envelope the Centaurus actually occupied low-altitude strike, carrier operations, colonial air policing, close air support in tropical conditions. No jet engine then in British service matched it on endurance, on reliability, or on the logistical simplicity of its fuel and maintenance requirements. The decision was not purely technical. It was doctrinal. Britain had decided what kind of air power it intended to project, and piston engines had no place in that vision, regardless of what they were still demonstrating in the skies over Korea and the jungles of Malaya. The Treasury's position reinforced the Air Ministry's. Maintaining parallel research, development, and production infrastructure for both piston and jet propulsion was a cost that post-war Britain could not indefinitely sustain. The defense budget was under pressure from every direction simultaneously. The Korean commitment, the nuclear program, the NATO obligation to maintain forces on the Rhine. Something had to give. The industrial logic was brutal and, in its own terms, coherent. Concentrate investment in jet propulsion. Accept the transitional capability gaps and close the piston lines before they consumed resources that the next generation needed. Patchway received the last substantive Centaurus production order in 1953. A batch destined for Sea Fury export contracts. After that, nothing of scale. The order book that had sustained 6,800 direct employees and a West Country supply chain of 4,000 more did not collapse suddenly. It tapered. Workshops were reassigned. Machinists who had spent careers grinding sleeve bores to thousandths of an inch tolerances were retrained, where possible, on the different disciplines that jet engine manufacture required. Where retraining was not possible, redundancy followed. Quietly, without headlines, absorbed into the general turbulence of a British defense industry in structural transition. Roy Fedden, the engineer who had originated the sleeve valve program and staked his professional reputation on its feasibility, was not present to witness any of it. He had been forced out of the Bristol Aeroplane Company in 1942, a decade before the Centaurus reached its operational peak, following a prolonged dispute with the company's board over management authority and the division of engineering responsibility. The circumstances were bitter. Fedden had built the engine division from a small team into one of the most capable aero-engine organizations in the world. The board concluded that his working methods had become incompatible with the company's direction. He left without a settlement that satisfied either party. What followed was one of the more quietly remarkable second acts in British aviation history. In the same year he left Bristol, Fedden was dispatched by the Ministry of Aircraft Production on a technical intelligence mission to occupied Europe, tasked with assessing the state of German aero-engine development. His report, comprehensive, technically rigorous, and deeply uncomfortable reading for those in Whitehall who preferred to believe that British engine technology led the world, identified specific areas of German superiority in high-altitude supercharging and fuel injection that directly influenced RAF procurement decisions for the remainder of the war. It was, in its way, a final act of service to an industry that had just shown him the door. Fedden spent his remaining years in government advisory roles and died in 1973. Having watched the engine, he originated Power, a carrier aircraft, to one of the last piston versus jet victories in operational history, an event he has not recorded as having publicly commented upon. Bristol's institutional response to the Centaurus's wind-down was characteristically unsentimental. The company did not lobby the Air Ministry to reconsider. It did not seek alternative export markets with the urgency that a contractor fighting for program survival might have mounted. It accelerated, instead, the programs that were replacing the Centaurus in its own facilities. The Olympus turbojet, the engine that would power the Avro Vulcan and later Concorde, was consuming the engineering attention of the most capable people at Patchway. The Proteus turboprop was under development for the Bristol Britannia. The Orpheus lightweight jet was being prepared for the fallen Gnat. Bristol was not mourning the Centaurus, it was building what came next. The grinding machines, those dedicated precision tools that Patchway's engineers had designed and built themselves in the late 1930s because no commercially available machine could hold the tolerances the sleeve valve demanded, were scrapped. There was no market for them. No other engine in development required what they had been built to provide. They were melted down with the same administrative efficiency that had governed every other aspect of the transition. What was lost operationally was not, in the Air Ministry's accounting, dramatic. The Hawker Hunter and the de Havilland Venom filled the fast jet roles that the Tempest had occupied. The Seahawk replaced the Sea Fury on carrier decks. The capability arguments were sound, at altitude and at speed, but the subtler losses did not appear in the Air Ministry's accounting. Loiter time over target, reduced. The Seahawk's Rolls-Royce Merlin burned fuel at a rate that cut effective endurance over the Korean-style target area by a margin that Fleet Air Arm planners noted and accepted as the cost of progress. Low altitude range in tropical conditions, reduced. The logistical simplicity of an air-cooled piston engine, which required neither the specialist ground equipment nor the fuel-grade precision that early jets demanded, was gone. The Fleet Air Arm flew its last operational Sea Fury sortie in 1955. After that, the carriers were jet decks. The last Centaurus engine left Patchway in 1957. No ceremony marked it. No minister visited the factory floor. No statement was issued. The production record was closed. The workforce dispersed. The line went cold. Orders fulfilled. Contracts completed. Program concluded. Bristol moved on. The engine did not get to. The Bristol Centaurus left no direct descendant in British military aviation. No engine succeeded it in the same role, built on the same principles, by the same hands. The sleeve valve radial, the technology that Fedden's critics had declared impossible in series production, and that Patchway's engineers had spent a decade proving otherwise, died with the program that had sustained it. Britain's aero-engine industry moved entirely into the jet age, and the accumulated knowledge of how to manufacture a sleeve valve to thousandths of an inch tolerance in volume production moved with it into retirement. But influence is not the same as inheritance, and the Centaurus left influence in places that were not immediately obvious. The thermal management principles that Patchway developed during the sleeve valve crisis of the late 1930s, the revised oil feed gallery design, the nitriding processes for hardened steel surfaces, the proprietary approaches to maintaining dimensional accuracy under cyclic thermal loading, fed directly into Bristol's industrial and marine engine programs of the 1950s and 1960s. The company's work on large, slow-running diesels for naval auxiliary applications drew explicitly on sleeve valve knowledge that had nowhere else to go. It was a quiet transfer from one division of the same company to another, unannounced and unrecorded in any public document. But the engineers who made it knew where the knowledge had come from. More significantly, the manufacturing discipline that the Centaurus program imposed on Patchway shaped the culture that Stanley Hooker inherited when he arrived from Rolls-Royce in 1949. Hooker was, by any measure, one of the most important aero-engine engineers of the 20th century. At Rolls-Royce, he had redesigned the Merlin's supercharger in 1938, increasing its power output by a margin that contributed directly to the RAF's performance advantage during the Battle of Britain. He had led the development of the Rolls-Royce Nene and the Derwent. When Rolls-Royce declined to offer him the position he believed his record had earned, he accepted Bristol's approach and moved to Patchway. He arrived into a facility that had spent 15 years solving a problem that the rest of the world's aero-engine industry had been unwilling to attempt. The Centaurus team's obsession with dimensional precision, the culture of a workforce that had built its own machine tools rather than accept that the tolerances it needed were unachievable, was not lost when the sleeve valve line closed. It transferred. It became part of the institutional character of the team that Hooker led into the Olympus program. Hooker recorded this debt explicitly. In his 1984 memoir, Not Much of an Engineer, one of the most candid accounts of British aero-engine development published in the 20th century, he wrote of the Centaurus engineers' approach to manufacturing tolerance as a discipline that had left its mark on how Patchway approached every subsequent program. The Olympus, which powered the Avro Vulcan from 1956 and Concorde from 1969, was built by an organization that had learned its precision standards on a piston engine that was already being phased out when Hooker arrived. The lineage is oblique, but it is real. The Olympus turbojet first ran at Patchway in May 1950, 3 years before the last substantive Centaurus production order was placed. For a period of approximately 3 years, both programs coexisted within the same facility, drawing on the same workforce, the same machine shop, the same institutional knowledge. The engine of the future and the engine of the past occupied the same factory floor. That overlap was not accidental. Bristol managed it deliberately, using Centaurus production revenue to fund Olympus development at a stage when Air Ministry contract support for the new engine was not yet sufficient to sustain the program independently. The Centaurus, in its final years, financed its own replacement. That is the institutional irony that sits at the center of the program's history, and it is one that the Air Ministry's accounting never made visible. The revenue from Centaurus export orders to Canada, Australia, Pakistan, Iraq, Cuba kept Patchway solvent during the critical early phase of Bristol's transition to jet propulsion. Without the Centaurus's export income in the period 1950 to 1954, the Olympus program's development schedule would have been constrained at precisely the moment it could least afford delay. The V-bomber that carried Britain's nuclear deterrent through the late 1950s was powered in part by the commercial momentum of the engine it had replaced. The honest verdict, to the extent that procurement history permits one, is straightforward. The Centaurus was not a failed program. It was not a procurement disaster. It was not cancelled because it underperformed, overran its budget, or proved incapable of meeting its specification. Every Air Ministry assessment of the engine in operational service, those that are available in the Avian ADM series at Q, record serviceability and performance figures that met or exceeded the original requirements. The engine was retired because the doctrine it served was retired. Britain chose to build a different kind of air power. That choice was rational, strategically defensible, and shaped by pressures, financial, technological, and political, that no single program could have resisted. What the Centaurus deserved and did not receive was a public accounting, a recognition in Hansard or in a white paper or in a ministerial statement to the House that something of consequence had been closed, that the men who had spent careers grinding steel to thousandths of an inch, who had built their own machine tools because the industry told them the job was impossible, who had kept Fleet Air Arm aircraft flying over Korea in conditions that no test program had anticipated, that those men and the work they had done warranted more than administrative silence. They did not receive it. The line closed. The records went to Q. The engines that survived went to museums. If you found this history valuable, give the video a like. It is the single best signal you can send this channel. And if you want more stories about the engines, the aircraft, and the decisions that shaped British military power, subscribe to UK Defence Archive. We'll see you in the next one. At 7:30 on the morning of 9th of August 1952, a Bristol Centaurus the Tech-10 turned a four-bladed rotor propeller at full combat power over the Yellow Sea. The aircraft it drove, a Hawker Sea Fury of 802 Naval Air Squadron, rolled into a turning engagement with a swept-wing jet and emerged from it with a confirmed kill. The engine ran. The sleeve valves held. The oil film between steel surfaces machined to thousandths of an inch did not break down. Somewhere beneath the aircraft, the Korean coastline passed in silence, indifferent to what had just happened above it. The Sea Fury recovered to HMS Ocean. The Centaurus was turned off, inspected and cleared for the next sortie. It was, in every respect, doing exactly what Bristol had built it to do, in a war that Whitehall had already decided would be its last.